We now discuss the solution of a problem from the section Linear Algebra. The problem is related to the properties of nilpotent matrices. This question has appeared in the CSIR National Eligibility Test held on 16th September 2022, and it is from the part C, and it carries 4.75 marks. The given question is, for a positive integer n greater than or equal to 2, let capital A be an n by n matrix with the entries in R the set of real numbers such that A power n square has rank 0. Let 0 suffix n denote the n by n matrix with all its entries equal to 0. Which of the following statements are true to the statement that A has n linearly independent eigenvectors? Which of the following statements are equivalent to the statement that A has n linearly independent eigenvectors? We are given 4 options. Option 1, A power n is 0 suffix n. Option 2, A power n square is equal to 0 suffix n. Option 3, A is equal to 0 suffix n. Option 4, A square is equal to 0 suffix n. We are given n is a positive integer greater than or equal to 2, and it is given A is a n by n matrix, n by n real matrix such that A power n square has rank 0. That is, the rank of A power n square is 0. Then, which of the following statements that are given in options 1 to 4 is equivalent to that A has n linearly independent eigenvectors? Let us now discuss the solution of the problem in detail. We have n is a natural number greater than or equal to 2, and A is a n by n real matrix such that the rank of A power n square is equal to 0. Now, the rank of A power n square is equal to 0 means A power n square itself is equal to n by n 0 matrix. And if A power n square is equal to 0n, then A is a nilpotent matrix of order n. So it is a n by n nilpotent matrix. Agreed. Let S be the statement given by, so S denotes this statement. The statement is A has n linearly independent eigenvectors. And whenever I say that a matrix has the property as, it means A has n linearly independent eigenvectors. Agreed. We move on to the next slide. Let us take an example. A is a 2 by 2 matrix whose first row is 0, 1, 0, 0. For this matrix, n is 2. It is a 2 by 2 matrix. N is equal to 2. For this matrix, A power n square is the 0 matrix. That is, A power 4 is 0, 2. Agreed. Correct. This is true. You can verify it. So, it is a nilpotent matrix of order 2. It is a 2 by 2 nilpotent matrix. And it is known that each eigenvalue of a nilpotent matrix is 0. Yeah, we know this. And for this one, 0 is the only eigenvalue, and it has only one eigenvector. You can compute. It is a very easy question. So you can compute the eigenvalue eigenvector corresponding to the 0, the eigenvalue 0, is a repeated 0, is only 1. That is, it has only one eigenvector. So, let's now move on to taking the option 1 first. A power n is equal to 0n. And similar argument is valid for option 2 and option 4 also. So, a power n, this is the statement that is given in option 1. A power n is equal to 0n. So, if A is this 2 by 2 matrix 0, 1, 0, 0, then A power n is equal to 0n. So, this statement is true here. And equally, the statements that are in option 2 and option 4 are also valid for n is equal to 2. And it has only one eigenvector. Only one eigenvector. But it is a 2 by 2 matrix. It has only one eigenvector. If this statement that is given in option 1, that is A power n is equal to 0 n, is equivalent to the statement S. What is S? The statement A has n linearly independent eigenvectors, then A must have n is equal to 2 linearly independent eigenvectors. But this is not so. Why? It has only one eigenvector. So therefore, your statement, if this statement is equivalent to the statement S, is not true. It's not true. So therefore, the statement given in option 1, that is A power n is equal to 0 n, is not equivalent to the statement S, that is A has n linearly independent eigenvectors. This is not true. It's not true. So this is not true. The above n is equal to 2 linearly independent eigenvectors is not true. Therefore, the statement given in option 1 is not equivalent to the statement S. And a similar argument is valid for A power n square and A is equal to 0 n, A square is equal to 0 n for the same matrix, 2 by 2 matrix 0, 1, 0, 0. So, by the same argument, the statements given in options 2 and 4 are not equivalent to the statement yes. Yes. Thus, the options 1, 2 and 4 are overruled. So therefore, option 3 must be the answer. But however, we have to prove it. So now, I will now state and prove a result. The result is a nilpotent matrix capital A of order n, where n greater than or equal to 2, has n linearly independent eigenvectors if and only if A is the n by n 0 matrix. Agreed? Let's write down the proof. Proof. Let A be a nilpotent matrix of order n. That is a n by n nilpotent matrix. And n is greater than or equal to. And it has n linearly independent eigenvectors. That means it has the statement yes. Agreed. And A is a nilpotent. And A has n linearly independent eigenvectors means A is diagonalizable. So A is diagonalizable if and only if it has n linearly independent eigenvectors. That we know. So this implies A is nilpotent and A is diagonalizable. Agreed. A is diagonalizable means A is similar to a diagonal matrix. So A is diagonalizable implies there exists a matrix, a invertible matrix P, such that A is equal to PDP inverse, where D is a diagonal matrix whose diagonal entries are the eigenvalues of A. On the diagonal entries of capital D, we have the eigenvalues of A. Agreed. Agreed. But what is A? A is nilpotent. And what do you know about their eigenvalues? All eigenvalues are 0. So, since A is nilpotent, all its eigenvalues are 0. Therefore, D will be a n by n 0 matrix. Why? On the main diagonal, the diagonal entries of this diagonal matrix are the eigenvalues of A A is nilpotent, all its eigenvalues are 0. Therefore, D is the n by n 0 matrix. Thus, you go and substitute. A is equal to P, D is 0 n, P inverse, that is A is 0 n. Thus, A is equal to P D P inverse is equal to P into D is 0 n P inverse. Multiply, this is n by n 0 matrix. Thus, you get A is n by n 0 matrix. That is, if A is a nilpotent matrix of order n and has n linearly independent eigenvectors, then it will be a 0 matrix. Agreed. Conversely, if A is a n by n 0 matrix, and obviously it is a nilpotent matrix, and every n by n 0 matrix is diagonalizable, obviously. So conversely, if A is equal to 0 n, then A is nilpotent and A is diagonalizable. A is diagonalizable if and only if it has n linearly independent eigenvectors. It implies A is nilpotent and has n linearly independent eigenvectors. Thus, the theorem is established fully. Hence the result. So, it's a nilpotent plus has n linearly independent eigenvectors if and only if A is the 0 matrix only. Let's now take the option 3. A is 0 n. Yeah. Now, by the above result, the statement given in option 3 is equivalent to the statement yes. That is, A has n linearly independent eigenvectors. So that is true. So therefore, the option 3 is true. The answer to this question is option 3. That is the detailed discussion of the solution of the problem from the section Linear Algebra, which is related to the properties of nilpotent matrices. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.